For thousands of years, farming relied on intuition and estimation, flooding a field and hoping the water reached the roots. But as global resources shrink, that guesswork is being replaced by precision agriculture. The strategy here is simple: providing the plant with exactly what it needs, at the right time, in the right place, and in the exact right volume. This table compares traditional methods against high-tech agriculture. By looking closely at the environmental impact and labor rows, we can see how modern systems enable 30 to 50% water savings while pushing crop productivity to its highest levels. To achieve that level of efficiency, you need a specific system architecture. Today, we are going to break down the 4 steps required to design an IoT-connected smart irrigation loop. Understanding how data moves through this loop allows you to move beyond traditional farming and begin engineering modern agricultural systems. Step 1 is establishing the overarching architecture. A smart farm relies on 3 integrated layers: the physical hardware in the field, the network layer transmitting data, and the application layer where decisions are made. While standard automatic sprinklers operate on a simple clock, a smart system actively monitors the crop's environment before taking any action. That brings us to step 2, deploying sensors. These act as the biological senses of the farm, continuously capturing microclimate data. You deploy different hardware depending on the data you need. Moisture and salinity sensors are placed deep in the soil near the root zones, while temperature and humidity sensors monitor the air above the canopy. Instead of a farmer manually sampling soil once a week, these probes generate a continuous data stream, transmitting environmental conditions 24 hours a day. Without this constant physical data anchoring the system, the rest of the high-tech cloud infrastructure would be blind. Step 3 is processing. The raw field data leaves the soil and moves to the IoT cloud, the brain of the operation. Here, the data is evaluated against strict rules. If we are growing tomatoes, we might set a rule that triggers action if the soil moisture drops below 60%. The AI algorithm evaluates that moisture deficit instantly and generates an execution command, removing the need for human observation. Remember that the AI only follows the logic it is given. Agronomists must accurately set these biological thresholds, or the system will execute an incorrect watering schedule. By automating the analysis, the IoT layer eliminates human delay, ensuring the crop receives exactly what it needs the moment it experiences stress. Step 4 is execution. The cloud sends a digital command back to the farm, triggering solenoid valves to open and release water. As seen in this photograph, crops can thrive even in a harsh desert environment. This is achieved through drip irrigation technology, pioneered by companies like Netafim in Israel, which delivers water directly to the plant's root zone. But the delivery itself is not the final step. The defining characteristic of Agriculture 4.0 is the feedback loop. As the drip system runs, the sensor continuously monitors the rising moisture. The moment the soil hits our target capacity, for example 80%, the cloud processes the new data and sends a shutoff command to the valve. Water stops flowing immediately. This precise control prevents wasted water and fertilizer runoff, which is the ultimate goal of this architecture. While traditional timers guess when a plant has had enough water, a responsive closed-loop system verifies it with physical data. We have now mapped the complete journey from environmental sensing to cloud analysis and automated execution. This specific architecture is what allows for the high yields and resource conservation that modern high-tech farming provides. For your next build, use this 4-step map to conceptualize adding an automated fertilizer injector, a process known as fertigation. Determine exactly where you would need to place electrical conductivity and pH sensors to make that second feedback loop function. Mastering these data loops allows you to transition from reacting to nature to engineering the future of food security.